Thank you very much, Chairman. So I came here once again and a little bit different positions now. Okay, so I am Suyeon Park from Center for Quantum Nanoscience and IBS, and also belongs to Ewha Women's University partially. And today I will talk about atom by atom electron spin resonance and toward spin qubits on the surface. Because thanks to Andreas, actually covering a lot of my pages also, so I will so skip some kind of my beginning pages, so don't be too much disappointed about that. I don't want a redundancy of the same contents. Okay, but I want to say these points just by 10 seconds, then, because this is one of the very, very high level and strong points why we use STM and what kind of advantage we can have from the STM experiments. So we can do atom by atom manipulation of atomic positions or following some kind of change of the chemical bondings or properties, also physical properties. So also here, we skip this page. Okay, so in this page, I first want to introduce the people working in the same type of projects, atomic spins and coupled spin systems, also using ESR-STM experiments, also series support, just like a chairman of this session. Okay, so 4 senior scientists are working in ESR-STM teams in the center, and also there are some postdocs, Yuwang, Yi-Chen, also some of the students are working together. And also there are quite a lot of alumni who are working in different places now. And also I want to say about this guy, Chris Luss, who is still working in IBM Almaden Research Center, and also some alumni from that lab, because these guys basically contributed to the developments of the ESR-STM techniques, and they published a lot of basic papers which were basically introduced by Andreas just in the previous talk. Also, we have a lot of guys, always we like the discussion and get advices and ideas from the guys in the world. Okay, so in this talk, I will talk about some coupled spin systems. Of course, I will start from the single spins, but I will move in the end to the coupled spin systems. And the spin qubits in STM is very unique in terms of it actually provides a bottom-up approach design of qubit system, which can be scaled down to 1 nanometer. And also, we can do the atom precision control of multi-qubit structures and interqubit couplings, because we can do the atom precision manipulation of the positions. So in this talk, I will firstly talk about the ESR in STM, where we control and measure the single atomic spins, but maybe will be quite shortened because of Andreas' talk previously. And also, I will move to the coherence of spin 1/2 single atom and molecules. Then the next step will be toward the spin qubits on the surface, and also what about more than 1 qubit on surface? Okay, thank you very much, Andreas. Okay, here on the right side, I am showing the titanium, which is in the free space. Then it should have the spin 1, because there are two electrons in the 3D orbitals. But on top of the M0 2 monolayer, especially 2 monolayer M0 surface, then people say that titanium has 1 hydrogen on top. So there is some kind of transfer of the charge, and then the spin states of this titanium looks like just 1/2. And the experimental evidence we have, so we now believe that this is spin 1/2 system, only 2-level systems, and very proper for the qubit operation. Okay, here is an image once again for 2 different types of titanium species, maybe having the 100 in each, and yeah, depending on the bonding site. Okay, then here I am showing some series of the ESI spectra measured at the different tunneling conductance. Then you can see the shift of the resonance frequencies for both oxygen side titanium and bridge side titanium. And here on the right side is the summary of the tunneling conductance dependence of the resonance frequencies. Then also we can obtain the information for the external field demand energy. Also, there will be a contribution of the field from the tip. So these are the kind of very basic informations we can obtain from the ESR-STM measurements. And also here you can see that the cross section of the extrapolation lines at zero tunneling conductance, which means the tip is very far from the atom. Then you can see the different values. It basically comes from the different G factors for oxygen side and bridge side titanium atoms. So there have been some kind of studies for this using the vector field. Okay, here I show a typical shape of ESR spectrum obtained from a titanium bridge side atom. And basically, this is the schematic of the configuration of the measurements. Then the spin states can be described very simply by the steady states in a rotating frame plus Raman precision. So this is some kind of textbook example of the spin state as a function of frequency. And then the measurements will be done by the tip spin, so we use the tunneling magnetic resistance or magnetic conductance. So the ESR current is the difference of the tunneling current for the RF on state and RF off states. And then we can use the magnetic conductance formula to obtain some kind of typical equations for the amplitudes of the peak and also lightness of the peak. And also here I show a typical example of the lightness measurements and some summary of the data. Then on the Y scale, you can see that the lightness actually ranges from here from 20 megahertz to 100 megahertz, but usually we can go down to 5 megahertz. It means that because the ESR energy resolution will be determined by this line width, so it actually corresponds to 0.02 to 0.4 microelectron volt, which is just roughly 1,000 times smaller than the energy resolution typically obtained from the normal scanning tunneling spectroscopy data. So this is a really, really big improvement of the energy resolution by implementing the ESR techniques into STM. Okay, then I move to somehow different steps, which should be the advanced steps from the Andreas talk. So how to control the spin quantum states? This usually can be done by pulsed ESR. So here, as you can see, then if we apply the pulsed RF signals to the tip atom junctions, then we can rotate the direction of the spins by the angle. Why it is moving? Okay, by the angle determined by the length of the pulse, and we can see the oscillation of the tunneling current. So here on the right side, I am showing the electronic systems, RF electronics installed to our system. At QNS, we actually installed 2 RF sources and 4-channel AWG arbitrary waveform generator, and we actually can do and control and measure the first vector RF control of coupled 2 spins. But here, because there is too much complicated to explain very details here, but in the very beginning of the first year's experiments, we have used one AWG, and which makes some arbitrary pulse forms, and they actually feed it to the RF generator, and we actually make the pulsed RF signals to the STM head to the tip. and using lock-in amplifier to measure the tunneling current. Okay, the first coherent control of single atom or molecular spins were performed for the titanium atoms on titanium atoms on magnesium oxide surface, and after obtaining the CWESR, then we now know the resonance frequency of the peak. Then by fixing the frequency at the resonance frequency, we obtain the beautiful Rabi, I would say beautiful Rabi oscillations like that. As you can see here, if we increase the RF voltage, then we can see the decrease of the oscillation period. But here on the bottom, and I am showing the Rabi rate and some coherence properties depending on the tunneling current. As you can see here, for our single atomic spins on MgO, then a Rabi period is limited or is larger than 20 nanoseconds, and also coherence is limited by 20 to 40 nanoseconds depending on the tunneling current. I will say some kind of details later. Okay, also we apply some standard schemes to measure the coherence of our spins, such as Ramsey fringe, and also spin echo, and obtain T2 star and T2 echo values, which is not that very beautiful, but anyway, we basically succeeded in applying most of the standard techniques to our single spins in STM. Also, soon after, we implemented the same techniques to the single molecular measurements and obtained very similar Rabi oscillations. And also, from a first ESR, such as Ramsey or spin echo measurements, then we obtained about 200 nanoseconds of the echo T2 time, which is not that different from the titanium. But anyway, this is the next step from the single atom measurements. And then the next step could be by the Rabi oscillation measurements or some kind of pulse techniques, we can control the theta angle, the polar angle of our spin, but how about the azimuthal angle? So to have or control exactly the superposition states of our qubits, we need to do the vector control. So the quantum logic operation basically needs the superposition and entanglement, but let's say entanglement is for the multiple spins, so I'm just talking about the single spin for the superposition. So here is a simple example how to demonstrate that we can do the vector control of the qubits. Then here I am showing the 3 pulse sequences, and the first pulse will initialize the direction of our vector, and in the second pulse, so-called we do the IQ control state rotation. So this actually determines the axis of XY plane. So that axis will be the axis of the second rotation. So if we take the pi angle to be 0, then the Y components will be projected to the Z axis. On the other hand, if we take the pi angle of pi over 2, then the rotation will be about different axes, then X components will be projected to the Z axis. So this is very technical things. And for the pi equals 0, then we obtain oscillation of the red bar in the scheme. But for the pi equal pi over 2, then basically all the vector will be in the XY plane. So the Z signal will be 0. So this is a simple but quite useful demonstration how to do the vector control of our qubit. Okay, then I want to move to some coherence properties we obtained from our pulse scheme. So here I'm showing the one typical measurements for the Han echo signal. In this case, for example, from the IMPC molecules, which is the spin 1/2. And then on the right side, I show the tunneling current dependence of the decoherence or coherence time. Here is the reciprocal of the coherence time. Then, as you can see, then the data actually nicely fitted by the linear line. So also, in the x-axis, the low tunneling current means the scattering of the spin states by the tunneling currents will be quite small. But on the other hand, on the right side, it will be very heavy. So interestingly, the data actually fitted by this linear relation very nicely. And we obtain a so-called P, which demonstrate which actually means the average scattering rate per electron. So this is 32% means that average 3 electrons, tunneling electrons, the spin states will be decohered fully. And also we measure the relaxation time like that. Also, in this case, the relaxation time T1 also depends linearly on the tunneling current. So from this kind of measurements, we actually make a table for several different species, ion, 2 different titanium cases, and also ion PC cases. Then we found some interesting features here. The T2 echo is almost very similar to 2 times of T1. But the T2 Rabi or T2 star, which is measured from the Rabi oscillations, and also Ramsey fringe, then which is much smaller than 2 times T1. This is very similar to many other spin systems or qubit systems. So we actually want to say, oh, what's happening there? So ESR over spin in tunnel junction of STM, poor coherence, a few hundred nanoseconds, and more seriously, the STM has some kind of disadvantage because only one qubit addressable at a time. So let's talk about this, why it happens. Because in the ESR STM, then the ESR over single spin is driven by the tip field, and also readout is done by tunneling current. So let me just skip these things and see what we have to do. What was some way to brighten the feature? So to enhance the decoupling from the substrate, then we should have a thicker decoupling layers and or exploring another insulating layers. And also we have to put some kind of effort to separate the driving from the readout. So this is also a way to increase the coherence of our spin, and also we can separate the measurement from the driving. And this is also will be a kind of way to have a spin qubits working independent of the magnetic tip. So this is very general case. So in many fields, then we can try to use the clock transition in this way. And then from these experiments, we obtain the T2 star values, which is 1 order of magnitude larger than the experiments using the normal transition frequencies, which actually changes the magnetic quantum number by plus minus 1. Also, we actually try to use the 3 monolayer AKMG, which is a little bit thicker than the normal case we have shown before. And then here we can see that on top of the 3 monolayer, we obtain a very, very large Rabi rate compared to that of 2 monolayer. And the T2 time, but T2 time is very similar. By doing the spin echo measurements, then we can see very improved, or this is not improved, this is already there. But we didn't see that before. But anyway, on top of 3 monolayer, the titanium atom shows much longer T2 time. And also, one more thing is that we actually try to decouple tunneling effect. So-called, we actually put the remote spins, which is not directly in the tunneling junction. As I am showing here, then in the STM image that you can see 2 titanium atoms, about 1 nanometer distance. And then these 2 titanium is coupled to each other. And we put 1 ion atoms very close to the second titanium. So in the schematics, then you can see that at the first titanium, ESR is driven by the tip magnetic field. On the other hand, the ESR of the second titanium can be driven by the magnetic field from the single atom magnet. Here, it is ion. And then, because this is two-coupled spin system, so we can we have to use the two-spin quantum state. But if the two titanium spins are coupled very weakly, then we can use the Zeeman product state to describe the quantum system. And also, on the other hand, we can use the first spin as the sensor spin and the second spin as a target spin, because we actually had a lot of trouble or struggling with the spin in the tunnel junction because of the tunneling current, the decoherence, and very fast relaxation. Now we can say that we are looking at want to control the second spin, and through the interaction between two spins, we want to measure the state of the second spin through first spin. So this is one example how to use that. And if we use two different frequencies, so-called double resonance techniques for the two frequencies, here, like the pulse schemes I have shown here, and then if by the first pulse, then we can transfer or control the population of these two states. And then the controlled populations will change the amplitudes of the transition for this guy. So if we keep changing the populations as a function of the pulse width, then we can see very nice oscillations, and which correspond to the control of the second spin. Also, if we measure the same type of things from other frequencies, then we can see another Rabi oscillations which has the opposite phase, because the blue oscillations basically are showing the change of the population of the ground state, P00, but the cyan oscillation shows the change of the population in the P01. So it should be opposite. Then we actually consider these two titanium atoms as two qubits, although the first qubit is under the tip and tunneling currents goes through that atom, so it is not good, I would say. But anyway, we can try to do this kind of CNOT gate operations with two qubits. So so-called the zero state of Q2 means, because in the summer states, then at very low temperature, we are doing most of the experiment at 0.4 Kelvin, and then the electron spin populations mostly exist at the ground state. So this we call Q2 is equal to zero state. And we measure the Rabi oscillations for these two frequencies, where only the spin states of the first spin changes, which is equivalent to this kind of cartoons. And then the result is like that. For the F1 at the low part, bottom part, then we can see the large, practically a large Rabi oscillation, which means that the population between 0, and 0, 1, 0 states actually changes by the controlling of Rabi scheme. But for the cyan, then we cannot see anything, because the 0, 1 state and 1, 1 state basically did not have a large enough population to show some signal. On the other hand, if we drive that by pi time, it means the inversion of the population of those two relevant states. Then do the same Rabi oscillation measurement for these two frequencies, which correspond to these situations. Then we can see the inversion of the signal for two measurement frequencies. It means that the population of the ground state, 0, states, is nicely transferred to one excited state to 0, 1 states. Then the upper transition will be more populated. Okay, so finally, I want to show some more complicated structures made by STM. So-called, we call it 5-atom structures, but practically it has 3 titanium atoms. So one atom is in blue here, and the other 2 atoms basically have ion each. Because here, because we always put the tip on top of titanium 1 and measure there, so the titanium 2 and 3 need a kind of driving field from such a kind of ion atoms. And then we actually named those 3 titanium atoms to Q1, Q2, Q3. Then here we couldn't do the perfect control of 3 qubit systems, but we actually wanted to check that we can do something, the coherent control, or that we could not reach it to the entanglement level. But so here we actually do the population control of these transitions and measure the signals from these 2 and obtain this type of oscillations, and also do the very similar things, but for the summer states of the Q3 equal to 1, and see the clear difference from the 4 corpus and upper side. So I don't want to give a very detailed explanation for this data because this is super complicated. They need 5 more minutes. But anyway, these actually experiments confirm us that we can deal with the 3 spins now, coupled to each other. Okay, so as a conclusion, our ESR STM actually is a kind of new spin qubit platform. And then from the first ESR, we characterize the on-surface qubits, and we also can do the nanostructuring. And finally, we obtain coupled spin qubits on the surface. And through the quantum gate operations, we actually start 1 spin and 2 spin and implemented double resonance techniques. And also, we extended our experiment to the 3 spins coupled to each other. So this is ongoing work. We are in this level now. Okay, thank you very much for your attention.
Thank you very much. Due to the limited time, we might have time for only 2 questions. Are there any questions in the audience?
Thank you very much for the talk. Would you explain again about the role of the metal nearby this the spin?
Okay. Okay, so maybe I can explain without the slide. Because usually we have a magnetic tip and 1 spin underneath that tip. So to drive the ESR, we need a magnetic field source somewhere. So for the single spin, then usually the magnetic tip plays that role. But for the spin, which is far from the magnetic tip, then it also needs some kind of source of the magnetic field, which can drive the ESR for this spin.
But then, but the metal cannot really generate the magnetic field by itself. So where does that come
What
from?
do you mean by metal?
Like iron nearby this.
I saw it, yeah. That ion basically plays the role of the magnetic field source to drive the ESR for the second spin.
Okay.
Yeah.
Okay. Thank you.
Thank you.
There is time for 1 more question. Okay, if there is none, then I will take this 1 minute. Sorry.
Okay.
What limits the scaling in that scheme that you showed here towards the end with the 3 qubits, basically? Can you scale that up? Because, as you know, the title is towards scalable. So, what's your opinion on this?
Because I already have shown the structure and position of each atom, so here we actually put very, very simple idea. Let's make a geometry of the atomic spins which can be coupled to each other. So there should be 1 atom which plays the role of sensor. Anyway, the tip should be on top of one titanium atom. Then maybe we can make 4, 5, but that could be the maximum in this kind of idea. So I think we should develop some more advanced idea to make more geometry, which can have more number of spins in the same space, because in this case, the control of the interaction between the spins are quite important. So there is the key points to move forward one more step toward the multi-spin systems.